let us take a look at our next subtopic, which is limiting reagents. What do we mean by limiting reagents? In chemistry, when reactions take place between two or more reactants, the reactant that is quickly used up before the other reactant runs out is called a limiting reagent. That is to say, between two reacting species A and B, if A should run out of reaction quickly before B, it means that A is the limiting reagent. And if B is still much available in the reaction, then it means B is the excess reagent. So, whenever two or more substances or reactants go into reaction, there most likely will be the reactant that is used up quickly as compared to the other reactant. So we simply say that the reactant that is used up quickly is called the limiting reagent or reactant, while the reactant that is still available for reaction is called the excess reagent. And this is what we mean by limiting reagents. Let us take a look at a pictorial explanation of that to understand what we are talking about more. So, when reactions proceed, the reactant that is used up, we say, is the limiting reagent, and the one that is still available is excess. So, limiting reactants simply limits the reaction that is taking place. Because once the limiting reactant has been used up, then it means that the reaction comes to an end. So in any given reaction, the limiting reactant or limiting reagent determines the amount of product that will be formed and also determines the length of time the reaction takes place. But the excess reagent is still there, much available for reaction to proceed. Let us now get to understand what we mean by limiting reagent and excess. Limiting reagent and excess is looking at this pictorial illustration of limiting and excess reagent. We have 8 car bodies and 48 tires. Each of these 8 car bodies needs 4 tires. So let us assume that the car bodies and the tires are our reactants, reactant A and reactant B. So when the car bodies reacts with the tires, each of the car bodies needs 4 tires. So when the reaction proceeds, eventually we have the combination of tires and cars. So when each of the cars takes 4 tires, it means we have exhausted 32 tires out of 48 tires. And before you know that, the reaction stops and we have an excess of 16 tires left. So, looking at this pictorial illustration, which of these reagents do you think, students, is the limiting reagent? Of course, I can hear you say 8 car bodies. So the 8 car bodies here is the limiting reagent. And the 48 car tires is the excess reagent. So it is excess because we still have 16 tires left over. But the 8 car bodies have taken the maximum quantity of tires that they need, and that is 32. When you multiply 8 by 4 each, we have 32 tires exhausted. So this is actually what we mean by limiting reagent and excess reagent. Now, away from limiting and excess reagent, we shall take a look at our next subtopic, which will be the last subtopic under stoichiometry, and that is percent yield. Percent yield is simply the ratio of actual yield to theoretical yield. And to calculate the percent yield of any given reaction, we use the formula percent yield equals to actual yield over theoretical yield times 100. Actual yield divides theoretical yield times 100. That is what we call percent yield. Actual yield is also called experimental yield. So let us take a look at how we can carry out calculations involving percent yield. Example 1. We are asked to calculate the percent yield of oxygen given that 40 grams of potassium chlorate, that is potassium triacylchlorate 5, decomposed according to the equation below to give 14.9 grams of oxygen. Now, we have been given the atomic masses of the individual elements making up that compound. So we are asked to calculate the percent yield of oxygen when 40 grams of potassium chlorate is provided, and then it gave 14.9 grams of oxygen. Like as I said before, in any question at all, you will need to understand and digest the question. By doing so, you will begin to comprehend the solution to that question. When you understand what the English is saying first, before we approach the mathematical aspect of the question, you will not have any challenge at all. So getting to understand the English will help us to understand the mathematics. So, to understand the English here, we are simply told that 40 grams of potassium chlorate is provided, and this potassium chlorate decomposed according to the equation by heating. And during this decomposition reaction, it produced 14.9 grams of oxygen gas. Then the question simply says we should calculate the yield of this oxygen gas, this 14.9 grams of oxygen gas, which was produced from 40 grams of potassium chlorate. That is a simple English. So, like we have said before, for any question, you will need to check for the balanced equation. If it is not balanced, we go ahead to balance. But if it is balanced, then we don't have problem. So, for the equation, as we can see, the equation is balanced. So we don't have problems balancing the equation. It is just to proceed to solving our question. And the question is to calculate the percent yield. So we have 2 potassium chlorate decomposed to give us 2 potassium chloride plus 3 oxygen gas. Now, it is clear that we are interested in 2 species, which are potassium chlorate and oxygen. So, like we've been seeing before, we are going to look at how to do this. To calculate the percent yield of oxygen, we have been told that percent yield is simply actual yield AY over theoretical yield TY times 100. If you wish, over 1. So, this is how to calculate our percent yield. And we are asked to calculate the percent yield of oxygen. So, how do we proceed? To do this, we will need to bring out the parameters given to us already. And the parameters are 40 grams of potassium chlorate. And we were told that potassium chlorate gave us 14.9 grams of oxygen. This 14.9 grams of oxygen, this is the experimental yield, which is also known as the AY, actual yield. That is to say, this experiment has been done somewhere. We were not there, but it has been done in the lab, and it was concluded that 14.9 grams of oxygen was produced from 40 grams of potassium chlorate. But our trouble now is we were told to calculate the percent yield of that oxygen gas produced, even though we were not there when it was produced. So, simply put, that the 14.9 grams is the actual yield, because that was what was produced when 40 grams of potassium chlorate decomposed. So, our trouble now is to find Ty. And how do we go about looking for Ty? It is to calculate the molar masses. So, to calculate our Ty, for oxygen, which we don't know, the theoretical yield, you can see the name theoretical yield. Theoretical yield means we are not doing it practically. It is by theory. That is to say, we are doing it here in the class. So, it is not being done in the lab. But AY 14.9 has been done in the lab. And that is why it is the actual yield or experimental yield. So, how do we go about calculating our Ty? To calculate our Ty, we will need to solve the molar masses of potassium chlorate and oxygen. So, from there we can get our theoretical yield. So, let us proceed. Just as we've been doing before, from the equation, 2 moles of potassium chlorate produce 3 moles of oxygen gas. 2 moles of potassium chlorate produced 3 moles of oxygen gas. So let us take it to mass. What is the molar mass of this compound? Though we've done this before, but for the purpose of clarity and to make it sink down into our memory more, let us do it again. 39 for potassium plus 35.5 plus 16 times 3 for oxygen. So this is potassium chlorate. And for oxygen, it is 3 into 16 times 2. We are trying to calculate Ty. That is theoretical yield. So to calculate our theoretical yield, we say we have to calculate the molar masses. And from there, we can get our Ty. So from the balanced equation, 2 moles of potassium chlorate is given 3 moles of oxygen gas. So let's just see. This will boil down to giving us 2 into 39 plus 35.5 plus 48. And that boils down to giving us 2 into 122.5. And that will give us 3 into 32. So, when we multiply that, we have 245 grams of potassium chlorate giving us 96 grams of oxygen gas. So, from the equation, from the balanced equation, it is seen that 245 grams of potassium chlorate gave 96 grams of oxygen gas. If that is the case, what we'll now say is that 40 grams, if 245 of potassium chlorate gives 96 grams of oxygen, 40 grams of potassium chlorate will give X of oxygen. How many oxygen will it give? So when we cross multiply, we have 245 times X is equals to 96 times 40. And we have 245X is equal to 3,840 grams of oxygen. And that will give us, dividing both sides by 245, dividing both sides by 245, we have 245 taking care of 245. Therefore, X will be equal to 15.67. 15.67 grams of oxygen gas. So this is what we call our Ty. So this is our Ty. So the theoretical yield for oxygen is 15.67 grams. Why? It is because from the equation, 245 grams of potassium chlorate will give 96 grams of oxygen. Now, if 40 grams of potassium chlorate were to be provided, what mass of oxygen will it give? From our calculation, you can see it will give us 15.67 grams of oxygen. But from the calculation done in the lab, it gave them 14.9 grams. So we have a difference of maybe 1 point or thereabout. So this gives us the difference between theoretical yield and actual yield. Now, the fact is that theoretical yield is always more than actual yield. Theoretical yield is always more than actual yield. In any percent yield question, theoretical yield will always be more than actual yield. So our theoretical yield gave us 15.67 grams, but their actual yield gave 14.9 grams. So it tells us that within experimental errors, they are having 14.9 grams. But our theoretical yield is giving us 15.6 grams. So the difference should just be not just maybe 0 point something, almost 1. Okay, the difference should just be around 0.7 or thereabout. So that is actually what we have. Looking at the difference between 15.67 and 14.9, that should be around 0.7. So you can see the difference isn't that too much. Maybe within experimental errors, they got 14.9. So our theoretical yield is 15.6. And I want to establish that in every question under percent yield, Ty must always be greater than Ay. Please, it is good we take note of this. Ty must always be greater than Ay. Ty is always greater than Ay in every question that had to do with percent yield. So let us proceed now to our solution. To solve our problem, let us proceed to solving the problem. So we have gotten our Ty. Let us now look at the percent yield of oxygen. Therefore, percent yield of oxygen O2 is equal to Ay, actual yield, over Ty, theoretical yield, times 100. So what is our Ay? The Ay is 14.9. And our Ty is just what we've calculated, 15.67 times 100. So our theoretical yield, our percent yield, will be equal to 14.9 times 100, which you can see over 1. That gives us 1490 divide 15.67. And our percent yield, therefore, will be percent yield of oxygen will be 95.08. 95.08. That's percent. That is our percent yield of oxygen. So this is what our percent yield is.